Okay, so now we've talked about determinants. And at this stage, the only thing I've told you about determinants is that they are numerical measures attached to any square matrix. But one thing should stand out is that evaluating them is quite a computationally demanding task. For example, I just imagine for a second that you were going to evaluate the determinant of a 7 by 7 matrix, and all that you had at your disposal was cofactor expansion. Well, you'd have to choose a row or a column to perform cofactor expansion along. Once you do that, you're going to end up with an expression that involves 7 6 by 6 determinants. And each of those 6 by 6 determinants, how are you going to evaluate them? You're going to need to use cofactor expansion again. And you're going to have to now choose another row or a column in each of those smaller 6 by 6 matrices and perform cofactor expansion along that row or column, whichever one you choose. Well, what's going to happen? You're going to get an expression involving 6 determinants of 5 by 5 matrices. So really, if you do the math, you're going to end up with 42 determinants of 5 by 5 matrices to compute. And each one of those 5 by 5 matrices is no joke either. There's still quite a bit of work, and that it's going to get even more and more complex by the time you work your way down to determinants of 2 by 2 matrices. So it gets explosively complicated very quickly without having to even go that large, because in the big scheme of things, 7 by 7 is not that large of a matrix. So the point is, while cofactor expansion is how determinants are defined, we'd certainly hope there's a better way to actually compute them. And that's what this section is going to be about, looking for shortcuts that we can take. And as you might be able to guess, that shortcuts is going to appear in the form of row reduction, right? So that's why we call it, this section is called determinants by row reduction. We're going to look at how to use elementary row operations to make taking determinants a bit easier. Okay, and we're going to start with a couple of observations. And these observations apply to any square matrix A that you might start with when you're going to now consider calculating a determinant. Well, the first remark says that if you have a matrix A that has either a row of zeros or a column of zeros, then the determinant of that matrix is just going to be 0. And before we go on to the second remark, let's look at this example here, which gives you a bit of justification for why that's true. So here we've got a 3 by 3 matrix, A, and it's given by these entries here. Here you can see it, this 3 by 3 matrix. And one thing you do notice is that it has a column of zeros. So why don't we choose exactly that column to perform cofactor expansion along? Right, so it's got a column of zeros. We have to choose a row or a column anyway. Why not choose that as our column to do cofactor expansion along? And what are you going to get if you do that? If we do cofactor expansion along the first column, we're going to get 0 times the determinant of the matrix 2, 7, 4, 5. And then our next term will alternate signs, so we'll have minus 0 times the determinant of 1, -1, 4, and 5. And then our last term, we're going to go plus 0 back to a positive. We'll have plus 0 times the determinant of this 2 by 2 matrix in the top right corner. And, well, what do you see? You see 3 terms. Each of these determinants are multiplied by 0. So 0 times this determinant minus 0 times this determinant plus 0 times this determinant. So having an entire column of zeros means every one of these terms is multiplied by 0, which, well, what's the result going to be? It's going to be 0. So that's the idea, and it applies to any square matrix. It applies to rows as well. Nothing different will happen. So if you have a matrix that has a row or columns entirely consisting of zeros, you don't have to do any work. Just make that observation, and you can immediately conclude that the determinant is 0. So that's the first observation we'll make. Now, going back up here, the second observation says the following. Let's read it carefully. Since the rows of A are the columns of A transpose, right? That's a true fact about transposers. The determinant of A transpose is equal to the determinant of A. In other words, taking the determinant of a matrix has absolutely no effect. Taking the transpose of a matrix has absolutely no effect on its determinant. So, well, let's look at an example to try to see at least a little bit why that's true. I'm not going to prove that to you in general, but we can at least look at one example and look at what happens. So here's a matrix A. That's a 3 by 3 matrix. Nothing's biased about 3 by 3 matrices. They just happen to be reasonably brief to work through, so that's why I've included them in these videos. But you could do this with a a 4x4 matrix after just to check to see if it also works. But let's take a look. You've got a 3x3 matrix here. So I've set up two determinants. I've got the determinant of A, which is exactly, you see A written with two vertical lines around it. The matrix A is right here. Then here I've got the determinant of A transpose. And you can check that these entries are exactly the transpose of these entries. So my claim is that those two determinants are going to be equal. And let's maybe break them down a little bit and see why that's the case. Well, let's do cofactor expansion of A along the first row and see what we get. So we're going to end up with 3 times the determinant of 2, -1, 1, and 2. Then we'll have minus 1 times the determinant of -1, -1, 0, and 2. Right? If I delete the first row and the second column, I'll have those 4 entries, which is exactly what I've put here. And then lastly, I'll have plus 0. I'm going to take the time to write this last term out, even though there's a 0 there, because I want to really show what happens. Because remember, this is a claim that I'm making about all square matrices A, that the determinant of its transpose is equal to the original matrix. So whether or not there's going to be zeros appearing, you can't count on that. So let's just write out all the entries and write out the entire cofactor expansion. So we'd have 0, and then I'd be multiplying by this 2x2 determinant down here. So minus 1, 2, 0, and 1. And I'm not actually going to finish computing that. I'm going to stop there. Because I really wanted to just write it out so we could see the appearance of that cofactor expansion more than anything. We don't need to actually work it out. Let's take a look now at the determinant of A transpose. And these entries, 3, 1, and 0, that first row, they also appear in A transpose as the first column. So let's actually compute cofactor expansion of A transpose along the first column. So what are we going to get? Well, we'll start out with 3 times the determinant of those 4 entries down at the bottom right corner. So 2, 1, -1, 2. Then we'll have minus 1 times the determinant of what entries? So -1, 0, and -1, 2. And then lastly, we'll have plus 0 times the determinant of these 4 entries up here, -1, 0, 2, and 1. Okay, so that's what you would get. Now let's compare these. The similarities that you see right off the bat are those coefficients of the determinants. Right? You have 3, -1, and 0. 3, -1, and 0. What about the 2x2 determinants themselves? Look at this one. 2 times, this is a 2x2 determinant, right? So I can use the typical formula. 2 times 2 minus -1 times 1. What do you have down here? 2 times 2 minus 1 times -1. What's the difference? The only difference is that the 1 and the -1 are in different locations here, but they're still getting multiplied and subtracted afterwards. So the multiplication of real numbers doesn't care about order. So that's really why this determinant and this determinant are the same, and their coefficients are both 3. They're the same as well. What about this determinant? You got -1 times 2. Well, down here you're going to have -1 times 2 as well to start out with. Then you're going to subtract -1 times 0. Here you're going to subtract 0 times -1. It's the same numbers being multiplied before you subtract. It's just they're in the opposite order. But again, multiplication of real numbers doesn't care about order. So finally, with the third one, -1 times 1 minus 2 times 0. -1 times 1 minus 0 times 2. The only thing that's different is the order of the factors in the product that you subtract, but you still subtract that same product each time. So each of those 2x2 determinants are equal. So as a consequence, the cofactor expansion of A along the first row is equal to the cofactor expansion of A transpose along the first column. So we don't have to work these out entirely just to see that they're the same. So how about we say it this way? So based on the formula for 2x2 determinants, these agree. Let's just put it that way, state it simply. These agree. So I mean this calculation and this calculation. So this whole expression and this whole expression. So that's really why, that's just one example, right? That's not a complete proof, but that's just an example to kind of show you a little bit of evidence, at least, that the determinant of A transpose is equal to the determinant of A. It's actually, if you wanted to prove it rigorously, you'd have to use a technique called mathematical induction, which I'm not going to cover in this course. It would take, it's fairly straightforward, but it's a lot of bookkeeping and it's a lot of notation to do. But it does hold in general, so you can take that as a fact and put it in your tool belt. Taking the transpose of a square matrix does not affect its determinant. This is the most important statement from this work down here, right? So those two observations are summarized or just illustrated at least by these examples. But it's not proof, but it's at least evidence. Okay, and the rest of this section is going to really look at how determinants are affected by row operations, exactly what this little heading said. So the first operation we're going to think or look at is interchanging two rows. That's one of the row operations you can do when you're performing row reduction. And so again, I'm going to stick to the 3x3 case just because it's reasonably manageable. It's large enough that it illustrates what happens in general, but it's small enough to still become manageable and not take forever to write down. So I've written down a general matrix A in the usual way, right? I've got little a to represent the entries, and I've got two indices. For each of them, the first index represents the row, and the second index represents the column for each of these matrices. And then, for each of these entries. And I've written now a matrix B, which you can see is similar. They're the same entries, but what's happened? You can see that the first row of A is actually the second row of B, and the second row of A is actually the first row of B, and row 3 in both of these matrices are the same. So what's the point of this? Well, the point is that you can obtain B from A by simply just interchanging rows 1 and 2. Okay, now let's take a look at what their determinants would look like if we did cofactor expansion. Well, if I take the determinant of the matrix A and I do cofactor expansion along the first row, you get exactly this. And I invite you to take a moment to pause the video if necessary and just check that that's exactly what's happened. I'm not trying to pull a fast one on you here. This is just literally writing out cofactor expansion of this matrix along the first row. Right, you've got A times this determinant, which is here, or A11 I should say, minus A12 here, and then times the determinant of these 4 entries put together here, and then finally plus A13, which is this entry, times the determinant of these 4 entries, and that's what this is. So don't take my word for it. Pause this and double check that that's what I've actually done. And then what happens in the next line? Well, I'm just doing the cofactor expansion of the matrix B, taking the determinant of this matrix up here. Okay, well, but here I'm just choosing to do cofactor expansion along the second row. Why am I doing that? Just because those are the same entries as were in the first row of A, and it just makes it a little easier to see why or how these two quantities are going to relate. But you can see that this is indeed doing cofactor expansion along the second row. Notice that the first term has a negative sign, because if I were to write out the plus and minus checkerboard here, I'd have plus, minus, plus, minus, plus, minus, and plus, minus, plus. So that's why you have minus, plus, and a minus here. So I didn't actually draw the checkerboard this time, but that's where the minus, plus, and minus are coming from here. Okay, and the rest just comes from the standard cofactor expansion. Okay, and in the next clip, we'll just take a look at how exactly these relate. But you should see some similarities already.